Hello, my friend. Welcome to my channel and my brand new video. Today, I'm here to captivate you once again. Why? Because our topic is turtles, but these ones can fly. For centuries, humanity looked to the skies with wonder, drawing inspiration from nature's most graceful flyers. The eagle, the hawk, the swift. The idea of a turtle, nature's quintessential slow-moving, earthbound creature, conquering the heavens seemed like a contradiction, a joke. Yet, the seeds for this aviation revolution were sown not in an engineer's lab, but in the ancient myths and fables of cultures worldwide. From the great world turtle of Hindu and Iroquois legend, carrying the weight of the world on its back, to Aesop's persistent tortoise, the reptile symbolized resilience, protection, and an unhurried, inevitable progress. Early aviation pioneers, obsessed with speed and agility, overlooked these virtues. It wasn't until the latter half of the 20th century, amidst the Cold War's escalating tensions, that a secret Pentagon think tank, inspired by these very legends, posed a heretical question. What if the ultimate aircraft wasn't the fastest, but the most survivable? What if, like a turtle, its primary strength was its impenetrable shell? This radical shift in philosophy marked the quiet, clandestine birth of the Colonian-class aircraft, a project so obscure it was merely a footnote in the annals of aerospace history, known only as Project Aegis. The 1970s were a period of profound paranoia. The doctrine of mutually assured destruction demanded not just offensive might, but near invulnerability. Traditional stealth technology was in its infancy, but Project Aegis took a different path. Engineers, studying the biomechanics of a tortoise shell, discovered its genius wasn't just in its hardness, but in its composite, layered structure, a fusion of keratin and bone that could dissipate immense force. This led to the development of biomimetic laminated armor, a layered alloy and ceramic composite that could withstand shrapnel and small arms fire far better than conventional aluminum airframes. The first prototype, the XA-1 Terrapin, was ungainly. Its wings were short and broad, its fuselage rounded and domed, earning it the nickname the Flying Brick on the Groom Lake test range. It was slow, fuel inefficient, and handled poorly. But during a live-fire test, when surface-to-air missiles detonated nearby, the XA-1, scarred and battered, remained airborne and operational. It was a eureka moment. For the first time, the military had proof that a turtle's strategy, sacrificing speed for an unparalleled defense, could have a place in the modern sky. The terrestrial turtle had proven its worth in armor, but the true revolution came from its aquatic cousins. A naval aeronautics team, struggling with the immense drag of carrier-based aircraft during takeoff and landing, observed a sea turtle. Its flippers, they noted, were masterpieces of hydrodynamic and aerodynamic efficiency. The same structure that powered it through water could be angled to generate incredible lift in air. This led to the bioactive wing, a radical design that could change its profile and camber more dynamically than any conventional flap or slat system. The result was the S-2 Loggerhead, a naval patrol and anti-submarine aircraft. Its unique wings gave it astonishing short takeoff capabilities, allowing it to operate from shorter runways and heaving carrier decks that would be untenable for other aircraft. Furthermore, the design was inherently stable in turbulent conditions, much like a sea turtle is stable in a rough ocean. The loggerhead didn't just fly. It swam through the air, a concept that forever blurred the lines between marine and aerospace engineering and opened up a new frontier for versatile naval aviation. As stealth became the paramount concern in the 1980s, the turtle form faced its greatest challenge. Its rounded, dome shape was a nightmare for radar-absorbent material application, designed for sharp, faceted edges. However, a material science breakthrough at MIT changed everything. Researchers developed a metamaterial carapace, a skin for the aircraft composed of microscopic geometric structures that could bend radar waves around the craft, rather than merely absorbing them. Like a turtle retracting into its shell and becoming a smooth, featureless rock, these aircraft could effectively disappear from radar scopes. The B-21 Mata Mata stealth bomber, named after the bizarre, camouflaged Amazonian turtle, was the first operational product of this technology. Its odd, lumpy, and non-aerodynamic appearance was a direct result of this radar-bending carapace, making it far stealthier than any flying wing. The turtle's form, once a liability, was now the key to becoming a true ghost in the sky. The end of the Cold War and the dawn of the 21st century brought a new existential threat: climate change and soaring fuel costs. The aviation industry was desperate for efficiencies. Turtle-inspired designs, long mocked for their slowness, were suddenly reevaluated. Their robust, spacious fuselages were perfect for housing large, high-bypass turbofan engines and vast fuel tanks. The dome shape, it turned out, created a stable, low-pressure zone above the aircraft that, when combined with the long, slender wings inspired by sea turtle flippers, resulted in significantly reduced induced drag. The Galapagos X-1, a proof-of-concept airliner, demonstrated a 25% reduction in fuel burn on transoceanic routes compared to conventional jets. It flew slower, yes, but its operational costs were revolutionary. Airlines, initially skeptical, began to see the wisdom of the turtle's pace. Relentless, efficient, and sustainable. The era of the fuel-guzzling speedster was ending, and the age of the skyfreighter was beginning. Introducing the public to turtle-themed aircraft was a monumental marketing challenge. For decades, aviation had been synonymous with sleek, predatory beauty, the sharp nose of the Concorde, the aggressive stance of an F-16. The first civilian models, like the Airbus Testudo, were derided as flying armchairs and austeres with wings. Their rounded noses, domed cockpits, and overall stout appearance were a cultural shock. However, a brilliant and unexpected marketing campaign turned the tide. Instead of hiding the design, they embraced it. Advertisements focused on safety, tranquility, and eco-consciousness, featuring calming music and taglines like, "Arrive relaxed, not wrecked," and "the smartest shell in the sky." The very ugliness became a badge of honor, symbolizing pragmatism and intelligence over fleeting aesthetics. The flying public, weary of cramped cabins and nervous landings, began to associate the turtle's shape with a safer, more comfortable journey. The perception shifted from awkward to endearing, from ugly to smart-looking. While passenger acceptance grew slowly, the cargo industry embraced the turtle revolution overnight. The fundamental architecture of these aircraft, a strong, pressurized shell with a wide, hinged nose cone for easy front-loading, was a freight operator's dream. The Atlas tortoise cargo plane became the backbone of global logistics. Its biomimetic armor allowed it to operate safely into rough, makeshift airstrips in conflict zones where other planes dared not go. Its fuel efficiency made long-haul cargo flights profitable even with volatile fuel prices. The ability to retract its landing gear into deep wells allowed for a perfectly flat cargo floor, maximizing space. These aircraft became the unsung heroes of global trade, the pack mules of the modern era, hauling everything from perishable goods to critical humanitarian aid. They proved that in the world of commerce, resilience and capacity were far more valuable than speed, solidifying the turtle's role as the workhorse of the skyways. The final piece of the puzzle came with the advent of advanced artificial intelligence and drone technology. If a single turtle-themed aircraft was resilient, a networked swarm of them would be unstoppable. Engineers developed small, unmanned turtlet drones. These units, with their hard shells and stable flight characteristics, were designed to operate in coordinated flocks, much like a school of fish or a herd of turtles moving to sea. A single mother shell command aircraft, a large turtle-themed drone, could deploy dozens of these smaller units. They could form defensive screens around valuable assets, create ad hoc communication networks over disaster zones, or conduct wide-area surveillance. Their simple, robust design made them cheap to produce and highly resistant to damage. This concept of distributed lethality and swarm resilience drew a direct line from the collective defensive strategy of a turtle hatchling frenzy back to the ancient instincts of the species, now playing out in the digital battlespace of the 21st century. Beyond the runways and boardrooms, the turtle aircraft embedded itself deep into the fabric of global culture. Children's cartoons featured heroic sky turtles saving the day. The distinctive silhouette became a symbol of environmental responsibility and thoughtful progress. Airshows, once dominated by roaring fighter jets, now featured silent, graceful demonstrations of the Aerocolonian flight teams, their movements synchronized like a ballet. The term turtle ing entered the lexicon, meaning to proceed with deliberate, unstoppable progress. They appeared in blockbuster films not as weapons of war, but as vessels of exploration and hope. This cultural adoption was the ultimate validation. The turtle aircraft was no longer just a machine. It was a symbol. It represented a maturity in human aviation, a move away from the violent, predatory imagery of the past toward a future built on sustainability, protection, and intelligent design. Today, as we stand on the precipice of commercial space travel and interplanetary exploration, the lessons of the turtle are more relevant than ever. The same principles of a protective, self-sufficient shell are being applied to next-generation spacecraft designed for long-duration missions. The Space Tortoise project envisions vessels with layered shielding against cosmic radiation and micrometeorites, with closed-loop life support systems that mirror a turtle's efficient metabolism. The slow, steady, and reliable Hohmann transfer orbit, the most fuel-efficient path to another planet, is the ultimate turtle strategy in the cosmos. The journey from ancient myth to the far reaches of space has been long and unexpected. It teaches us that inspiration can come from the most humble of places, and that true strength often lies not in the ability to strike fast, but in the resilience to endure, to protect, and to persevere. The skyways belong to the turtle, and soon, perhaps, the starways will too.